Hello again. So the purpose of this video is to prove a single theorem. It's to prove theorem 3.2.1, which says that, if U is a subset of R and P is an R, then P is a limit point of view if and only if there exists a sequence xn such that for every n, xn is in U minus P, and which satisfies that xn converges to P. So there's the thing that I'm going to try to prove today. Let's go ahead and prove it. It's theorem 3.2.1. So it's an if and only if theorem, so I need to prove two things. And let's just get the setup out of the way. Let's let U be a subset of R and P be an element of U. So I need to prove that P is a limit point implies the thing about sequences, implies the existence of a sequence, which has some properties. And I need to do the opposite. So let's do the forward direction. Let's assume that P is a limit point of U. And let's go ahead and recall what that means. That means that for every positive number delta bigger than 0, there exists some element x in U such that x is not equal to P and the absolute value of x minus P is less than that positive number delta. And this x depends on the choice of delta, right? It comes after the declaration of for all delta, so it's allowed to. I need to find a sequence of element, xn, of U different from P, such that x sub n converges to P. And let's just scroll up and check that that actually agrees with what the theorem says. So theorem 3.2.1. I need to find a sequence xn such that for all n in n, xn is in the set U set minus P, and which satisfies that xn converges to P. Cool. So there is, in fact, what I want to show. So let's try to come up with that sequence. On the way, well, I know something is true for every delta, so maybe I'll take a sequence worth of deltas. Each of those deltas will give me an x. That'll give me a sequence worth of x's. That should do the trick. So here's a sequence worth of deltas. Let's let delta n be 1 over n. Is that a positive number? Yeah, sure it is. So that means I can take that to be this delta. So I can apply this result because P is a limit point of U. I see that there exists some x in U. I'll call it x sub n because there's a different x for each delta, a different delta for every n, such that the absolute value of x sub n minus P is less than two things. Xn is not equal to P, and the absolute value of xn minus P in absolute value is less than delta n, also known as 1 over n. I now need two things. I need to know that I need to show that the limit of xn is equal to P, and I need to know that for every n, xn is in U set minus P. So let's just do that. So on the one hand, like, the limit statement is super obvious and you could prove it using any technique you want. Maybe you would use the squeeze theorem. I'm going to resort to an argument from definition just to make sure we remember definitions. So let's consider any epsilon bigger than 0. Let's let big N be something that we get to pick. We'll consider any little n bigger than big N, and the absolute value of x sub n minus P, by assumption, is less than or equal to delta n. Delta n is equal to 1 over n. But little n is bigger than big N, so 1 over little n is less than 1 over big N. And can I find a choice of big N that results in that being equal to epsilon? Of course I can. Big N equal to 1 over epsilon would do the trick. So that means that the limit of x sub n is equal to P as claimed. Next, I need to show that for every natural number n, xn is in U set minus P. Well, consider any little n in the natural numbers by our choice of xn. We know that this is true. We see that xn is in... Oh, nope. That's what we need to show. I know that xn is in u, and xn is not equal to p. Xn is in u, and xn is not equal to p. Oh wait, but that's exactly what it means to be in u minus p. Thus, xn is in u set minus p as needed. So that completes the proof of the one direction. Let's go the reverse direction. Let's assume that there exists a sequence xn such that for every n in the natural numbers, xn is in u minus p, and such that xn converges to p. I need to show that p is a limit point of u. That is, I need to show that for every delta bigger than 0, there exists an x in u such that absolute value, forgot one important bit, such that x is not equal to p, and absolute value of x minus p is less than delta. So this number delta, well, that's what I need to show. So where do we start? We start by considering any delta bigger than 0. I need to come up with a choice of x that comes from that delta. So let's consider any delta bigger than 0. I know that xn converges to p. So if I give you a positive number and tell you that a sequence converges to p, then I get something automatic. The definition of the limit now tells us that there exists some big N such that for all little n bigger than big N, absolute value of xn minus p is less than delta. Let's consider any little n bigger than big N. Then I get the conclusion that the absolute value of xn minus p is less than delta. Oh, neat. So that gives me this conclusion for that choice of x. Let's see what else we know. Let's see. For all n in n, xn is in u. So that's good. In fact, xn is in u minus singleton p by this. Thus, xn is in u, and xn is not equal to p. Nice. So, let's see what we've done. So, for any delta bigger than 0, we've constructed an element, xn, of u, such that xn is not equal to p, and, sorry, I'm writing too big for that space, absolute value of xn minus p is less than delta. Oh, neat, that's exactly the definition of a limit point. Thus, p is a limit point of u as we claimed. Cool. So I'll stop this recording right here. The next result will take more time to prove.